All right, Spartan fans, 2.1 part 2 and 2.2 limits involving infinity, book and calculator. So in the last video, even though the title was rates of change, we didn't really talk about anything involving a rate of change. So let's look at that now. Remember that rate of change is a fancy word for slope. So if you have something, some point x, f of x, and another point a, f of a, the rate of change is the f of a minus the f of x all over a minus x. And of course, the order doesn't matter. Let's look at something more complex, of course. And instead of saying x and a for our 2 points, let's look at, you have some point x, the f of x. And instead of using a, let's talk about using h. So you have some point x plus h, comma, and the f of x plus h. So what does this look like on a graph? So I'm just going to draw a, little sketch here. You have some point x, and it has a correlating y value, fancy, call it f of x. And you have some point x plus h. So the difference between x and x plus h obviously is h. And it has some corresponding f of x plus h. Okay, so like such and like such. And this is going to become important because we're going to be looking at time intervals. And we're going to be looking at distance and how fast things go, velocity and acceleration, et cetera. And it kind of all starts from this concept right here. So the rate of change in this particular case would be the f of x plus h minus the f of x all over x plus h minus x. Yeah. Do I have that right? F of x plus h minus. Okay. And then sometimes what happens is, well, not sometimes, all the time in this particular case, the x is going to reduce out. So you're going to end up with the f of x plus h minus the f of x all over h. And so this actually represents rate of change. It's just different from how you're used to saying it. So let's apply this to a word problem. So if it interests you, I'm going to do page 64, number 58. And of course, you'll be doing 57 for your homework. Okay, so we have a free fall on a small airless planet. Phoebe should be on this planet. A rock released from rest to fall on a small airless planet falls at y equals g t squared meters in t seconds. G is a constant. Okay, so it says, suppose the rock falls to the bottom of a crevice 20 meters below and it reaches the bottom in 4 seconds. So 20 meters in 4 seconds. So I don't think it takes us long to figure out that that is 5 meters per second. This represents its average speed. It is not necessarily falling at 5 meters per second the entire way down. Maybe it's falling at 7 meters per second for part of the way down, and maybe it's falling at only 3 meters per second as another part of the way down. So this is just its average. It's not like in a car where you're on cruise control. So the car on cruise control, sure, you have a you can monitor your speed and you can say, oh, well, from mile marker 1 to mile marker 6, I went 60 miles per hour on my cruise control. But if you look at when a car merges from from the, what do you call that? I don't know what you call it, the merging lane, but you're getting onto a highway and initially you floor it because you need to speed up. Your car needs to go fast so that you can merge onto the highway. You can figure out your average speed, but the car isn't going that average speed for every second along the way. So 5 meters per second for an average. Let's find out what G is. That's probably going to become pretty important. So we have 20 equals G time is 4 squared. So G is going to be, I'm going to use a decimal, 1.25. I prefer the fractions, but for the word problems, I'm going to use the decimals. So we have that Y is equal to 1.25 T squared. So this is your equation. And 5 meters per second is your average speed. Okay, that's all well and good. But what we really care about is with what speed did the rock hit the bottom? With what speed did the rock hit the bottom? Okay, well, the easiest way to figure this out is, let's say that the rock kept going. Trust me. So I have some, this is going to be 4. I'm just going to draw some random graphs. So this is time. And this is going to be height above the crevice, I guess you want to say. I don't even know how to spell crevice. CRE. Okay, so it's starting at a height of 20 meters and it's going to fall and bam, there we go. So at time 4 seconds, its height above the crevice is 0. Well, let's try and figure out a rate of change here. So what I'm going to do is, let's say that the rock kept going. And this is going to be my F of 4 plus H. So if this is my 4, trust me. So let's plug into our rate of change formula. So this is going to be the F of 4 plus H minus the F of 4 all over 4 plus H minus 4. You might be a little bit confused where that just came from. Let's write the points off to the side here. So I have 4 and 20. And then I have 4 plus H and the F of 4 plus H. Okay, so 20 represents the F of 4. So that's going to go here. So, okay. So I know that my F of X, 1.25 T squared. Okay, so here we go. Let's plug in. So I have 1.25 T squared. So this is now going to become 1.25. T is now 4 plus H squared minus the F of 4. We've already done that. The F of 4 is 20. Four minus 4 is 0. So we're left with H in the denominator. All right. All right, let's multiply this all out. So this is going to be 1.25 times 16 plus 8h plus h squared minus 20 all over h. Okay, pause the video, do it on your own. Okay, so that's what you get. Oh my gosh, what is all this? Who cares? All right. So it was 4 seconds when the rock hit the 20, dropped 20 meters. Had it kept going, well, I want this h, I want 4 plus h to be as close to 4 as possible. I want this space right here, I want h to be as close to 0 as possible. Guess what? Let's find the limit as h approaches 0. That is 10. So at the instant that the rock hit the bottom of that crevice, it was going 10 meters per second. Make a note to yourself. You know, I talked about knowing that the limit of sine x over x is 1. Instantaneous velocity. The f of x plus h minus the f of x all over h. And you're going to find the limit as h approaches 0, which is what we just did. Just did fancy rate of change. And then we want h to be as close to 0 as possible, because isn't x plus 0 x? And so in this particular problem, 4 seconds, we want h to be as close to 0 as possible. There you go, 10 meters per second. I'm going to review how to graph a piecewise function. And we will look at several graphs on the calculator and finding limits. Okay, so let's graph. The f of x is equal to 1 minus x squared, 2 x not equal to -1, and x equals -1. If you know your parent functions, this is going to be a no-brainer. 1 minus x squared is an upside down parabola shifted up 1. This is a reflected parabola shifted up 1. 2, when x is 1, it's just a point. -1, 2. So -1, 2, and that's going to be a closed circle. So this is the same thing as -x squared plus 1. So this is an upside down parabola shifted up 1. I'm going to do it in pencil first, and then I'm going to draw over it. I started in pencil, you don't really need it. So if it's shifted up 1, it goes boom. And then normally here, this x-intercept, I would have a closed circle, but it's not included. 1, 2, 1, 2, 4. You need to have nice graphs on graph paper. And there you go. And let's just review. The exact value does exist. Let's just look at -1. Clearly, that's the interesting point. The f of -1 is the closed circle. The limit from the left is 0. The limit from the right is 0. The overall limit exists. The limit as x approaches -1 of this function is 0. Let's review end behavior. You have something like the f of x is equal to -2x to the 5th minus 3 over 4x squared. We care about the lead. If you reduce this, you would get -x cubed over 2. So the end behavior for this is up, down. It's a reflected cubic. So if you memorize that all from last semester and you don't remember it, that's because you memorized it. If it's even, if the degree is even, up, up if A is positive, if A is greater than 0, and if A is less than 0, it is down, down. If it's the degree is odd, A is positive, it is x cubed, down, up. And if A is negative, it is up, down. It's going to be critical when we're finding limits. Asymptotes. So if you have something like 1 over x, the horizontal asymptote is at y equals 0. And if it is something like, oh, how do you find what you call it? Horizontal asymptotes. So here's, oh, this x equals 0 as well. There's an asymptote at x equals 0, and there's an asymptote at y equals 0. And of course, we care about asymptotes now because we're talking about limits. If you have something like ax plus b over cx plus d, verticals, how about this should be an x? It should be an x. Okay, you have vertical asymptotes at x equals -d over c. I'm totally just making up these letters, but where's the denominator 0? You have x-intercepts. Where's the numerator 0? So that's going to be -b over a 0. You care about the numerator. Y-intercept, of course, is at b over d. Make x 0, you're left with b over d. And then, of course, we care about is it oblique, the what you call it, the end behavior. So is it oblique, whatever. So if the degrees are the same, so if the degree of the numerator is equal to the degree of the denominator, hopefully you're a step ahead of me. The degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is at a over c. If the degree of the numerator is less than the degree of the denominator, if the degree of the numerator is less than, then it's going to be at y equals 0. I want to make sure I have that right. Numerator less than denominator. Yeah. And if the degree of the numerator is greater than the degree of the denominator, then it is either oblique. I just say it models end behavior. If it's exactly one more, if the degree of the numerator is greater than the degree of the denominator by 1, x cubed plus who cares over x squared plus who cares? If it's greater by 1, if it's x to the 4th over x cubed, x to the 5th over x to the 4th, whatever, that's oblique and it's a line. That's if it's one more. This is important because if you look in your book, page 72, all review. So I'm not going to do any of these. All of the homework problems, page 72, number 17 to 38, all require that you know how to do end behavior, finding asymptotes, etc. Let's look at problems though that you don't quite know. So I'm going to do something like let's do number 10, where you're asked to find the limit as x approaches 2 from the left of x over x minus 2. It doesn't hurt to know what the graph looks like, but this has an asymptote at x equals 2. That's what we care about. There's an asymptote. So as I'm coming at, I have no idea what it looks like other than there's an asymptote at 2. So the question becomes, as I'm approaching 2 from the left, I'm either going to approach infinity or I'm going to approach negative infinity. It's one of the two. When you're approaching an asymptote, it's got to be either positive infinity or negative infinity. So pause the video, plug it into your graph. We could have done this by hand, but it's really about plugging into your calculator and doing a little bit of check. So we can see that as I'm coming from the left, the graph is going to negative infinity. How can you tell that on your table? So I have my table as by 0.01. I don't really think I need that. So I'm going to start at 0 and I'm going to go, actually, no, let's leave it at 0.01. So let me go to my table and I want to know what's happening as x approaches 2 from the left. It's going to be a long time before I get to 2. So I'm going to go back to my table set and start at 2, which of course will say error. Yeah, it says error. So as I'm approaching 2 from the left, that means negative values, 0, 1, positive values. So as you can see, I'm just going to go back to 1.9. Getting closer and closer and closer and closer to 2. Those y values are getting bigger in the negative direction. So when the book tells you to use tables and graphs, this is what they mean. So it's negative infinity. And I said something before I started to graph it that's really important. When you have a vertical asymptote, so if x equals c is a vertical asymptote, then the limit as x approaches c from the right of the function has to be either plus or minus infinity, and same thing with the left. As you approach from the left or the right, either way, it has to be either positive or negative infinity. That's it for today.